Greetings. Let's continue on with our lectures and our lessons on anatomical kinesiology, human movement specialists. I'm gonna make you guys. First thing I want to show you guys is a cool picture to emphasize our point about applying global and local references. So if you recall, global references are fixed planes, axes, straight line dimensions, and rotational dimensions. Like a compass is fixed, right? The straight line dimension of north always points the same way no matter how you move, okay? North, south, east, west is fixed regardless of how you move. I told you that our joints are locally referenced, and that globally, when you're outside of a classroom, because a classroom you could set the front and back of class, the sides of class, the up and the down. Outside of the classroom in the real world, really the only things we have fixed is ground and gravity. We have the gravity that's always going to be influencing in the same direction no matter how we move, and the ground, which is typically, what if you're in the Rocky Mountains? All right, I get it, but we're not. We're in Lafayette, everything flat. So what I wanted to show you is this really cool picture that I found of a pitcher. Okay, I'm a Mets fan, so this is a Brave player. But this is a good illustration. So globally, no thanks news, globally you would say he's throwing overhead, over the top, and you're using a global reference because you're using the ground and you're seeing that he's throwing over the top. Now, here's where illusions come through. Just because his hand is 180 degrees from anatomical doesn't mean his shoulder has rotated 180 degrees from anatomical. That's where experts in human motion can see the illusions and the trap. So he's not abducted 90 degrees. He's actually abducted about, 180 degrees. He's actually abducted about 90 degrees. So if we looked at his trunk, like this was a straight line, look how he's sidearm. All pitchers throw sidearm because that gives you the most mechanical advantage of getting the most velocity of your distal segment, such as the hand. He gets overhead because he leans his trunk over. And so if I have my arm out and I lean my trunk, my hand is going to rotate globally more than 90 degrees. So globally, I am at 180, but locally, I'm still at 90. Okay? So that's a good example of why we have to understand the difference between local and global referenced concepts. Because if you don't understand the difference, you may think that this person's shoulder is abducted 180 degrees, but it's not. I'm covering his feet so that it doesn't give, see, he's sidearm. Okay, all right. Now, moving right along, let us continue down this road of understanding. Today, I'm going to get into a concept, and then we'll move on to bones and joints and that kind of stuff, all right? And then we'll apply it. So the first thing I want to talk about is what exactly a joint is. This has nothing to do with drugs. It has everything to do with the human body. And a joint is a articulation. What is an articulation? If anybody's ever played with Legos, you know what an articulation is. If you have one Lego block, it's just a Lego block. If you have a second Lego block, it's just a Lego block. But if you connect the two, you have an articulation. And the articulation is a noun. It's a concept. It's a coming together. What is a border? All right, what's a border? You're right, it's a coming together. It's an articulation between two states, two parishes, two counties, two countries. And so a border is not necessarily it's a thing, but it's more of a concept because it's an articulation between two things. And that's what joints are. So let me get a little prop here. So let's say for the ankle joint, okay? The ankle joint is it's a concept. It's an articulation between the talus and the tibia and the fibula, and there's like this water balloon. We call it a capsule, but it's a water balloon that kind of encapsulates the joint. It makes sure that it has oil and fluid, not oil, but fluid to for viscosity, right? So that we have a fluid movement. The more fluid we have, the less friction we're going to have, the less wear and tear we're going to have. And then that water balloon capsule has thickened areas of that capsule that we call ligaments. That's what a ligament is. A ligament isn't necessarily one rubber band or one rope. It's actually a thickened part of this capsule that encapsulates these joints. So a joint itself, like the ankle joint, is a concept. It's this fits into this, and it allows motion. But the actual Lego blocks that form that construct are bones. Okay? So we start with bones. And those bones come together to form articulations or joints. And then those bones can move about the bones, and we call those positions in motion. Okay? Now, here's where things get a little different. When I was in college, working on my doctorate at Auburn, in biomechanics, I had class with engineers. A lot of industrial and systems engineers had same classes with biomechanists. And one of the things that the engineers would always say is they were like, "We don't like your world." And I'm like, "What, dude? Is it because I'm from Delcom?" They're like, "We don't know what Delcom is, but we don't like your world because in engineering, you think about a door, right? So like, watch, see like that door. You think about that door and the articulation that is that door and the wall, two pieces that articulate together, the joint, the hinge. So if you think about applying our concepts, you'd have a polar axis and the door would rotate in transverse plane, right? Transverse plane about a polar axis. Now the engineers love this system. Why? Because the door is always going to move about the wall. The wall never moves. The wall is fixed. Our doors are not like that. And you're like, what? The reason my engineer friends didn't really like biomechanics is because in our body, yeah, we have a lot of times the door move about the wall, and we have a name for this motion too, right? Open, close, open, close. When the door rotates this way, we call it open. How do I know? Because I could get through it. And when it does this way, we call it close. Well, for our bodies, we have a similar concept. Let's say I'm moving my elbow the same way the door moves, okay? Open, close, open, close. For my elbow's perspective, that's extension, flexion, extension, flexion. This is why the engineers hated biomechanics, because I don't have to just move the door. I can open and close or flex and extend by keeping this fixed and moving the humerus. Extension, flexion, extension, flexion. You think about doing a row, right? Your arm doesn't go anywhere. Your arm stays still. Flexion, extension, flexion, extension. You don't have to move it like this. So my point is that for the knee, you can have knee motion, you could have knee motion like this. Flexion, extension, flexion, extension. And that's probably how you were introduced to knee joint motion. What I'm trying to show you is that joint motions are a relative change between two or more bones. It's a marriage, it's a relationship. And it doesn't just have to be this bone moves about this bone. Flexion, extension, flexion, extension. So when you're given an example of flexion and extension, it's not the rule. You can still have flexion and extension by moving the other bone. Now, here's where it gets tricky. Globally, this is why we do not analyze joint motions with global references. Globally, this flexion had a segment rotate the exact opposite global spin as this segment. Two different global spins, but the same local spin. Flexion, flexion. Well, give me some, that doesn't make sense. Give me some practical examples. I kind of gave you one last time with the cap and the bottle, right? Cap spins this way, and we call it opening. But guess what? I could also open it by spinning the bottle the other way. Two different global spins, but the same local spin, opening. Open. Same thing with the door. I can't use that door, but I could use this door. We're going to look at it in terms of a book. If the book is like this, the book is closed. And if the book is like this, the book is open, right? So let's look at two different ways we can open the book. Option number one, rotate the cover comme ça, globally like this. Or keep the cover fixed and rotate the rest of the book the opposite direction. It still gets me to the same place. A to B is the exact same as A to B from the perspective of the book. It gets me to the first page, okay? So that is something I need to implant in you guys, is that in human motion, you guys may have been introduced, you should have been introduced to basic human movement things like flexion, extension. But my job is to show you that flexion and extension, that looks like it's moving, and it is. That's the door moving about the wall. Open, closed, open, closed. I got it. But there's a lot of motion that occurs where the door is moving about the wall, is moving about the door. You can imagine this if you had I don't have one with me, but if you had like a little play set where you can keep the door fixed and you could just rotate the little play set. Open the door, close the door, open the door, close the door. Or keep the play set fixed and open the door, close the door, open the door, close the door. Okay? So those two things occur in opposite global directions, but the same local direction, the same change in angles locally. Okay? So what do I mean by that? Well, a couple examples is getting in the fetal position, right? I could be standing and I could get into fetal position from my knees like this and my ankles like this, okay? Or I could be off of the ground and get into fetal position like this. In other words, I could bring my femur down, like if I'm going to squat down, or I could bring my tibia and my fibula up. Two different global directions, same end result, fetal position. From anatomical to fetal flexion. From anatomical to fetal flexion. From anatomical to fetal flexion. So I think a lot of times people get caught up with wanting to hold on to these global references because these are the ones we are most that we experience the most in our everyday lives. We experience global references. Up, down, left, right, rises in the east, sets in the west. But what we don't necessarily experience is local concepts of similar change. Okay? Let me give you one more example of what I'm trying to talk about. If you had a runner, let's say a jogger, and they were going, I'm trying to pull up a photo to help complement my mill. So let's say you had a jogger jogging east, okay? They're jogging east, and let's think about what's fixed and what's moving, okay? So the ground is fixed, jogger is moving east. There's a change in motion, okay? Now what I'd like for you to imagine is a fixed runner with a movable ground. And if this treadmill, if the person was pointing east, in other words, the treadmill was in a direction where the person would be running east, they would still be running east. But what's happening is the ground would actually be moving west. So east and west may be a bad example. Positive and negative X would be maybe better, right? In other words, the same change, he's still running in the same direction, whether he stays still and the ground goes that way, or the ground stays still and he goes this way. Cool? All right. If you didn't understand that example, hit me up. Or if you understood the other examples and you didn't understand that example, don't worry about it. Just stick to the ones that you get and understand, okay? I like to offer up a lot of different analogies because sometimes you never know. Analogies are like a box of chocolates. You never know what you're going to react to. Okay, let me give you another example here with my upper arm bone, okay? So review from anatomy. We have our humerus here, and here's our ulna. Here's our radius. We have some carpal bones that articulate. We have some interphalangeal joints here. These are your knuckles right there, these guys, your metacarpal interphalangeals. So you have a lot of joints. And remember, joints are just articulations between bones. So you have endofetal, outofetal, flexion, extension, flexion, extension, flexion, extension, flexion, extension, flexion, extension, flexion, extension. So let's look at different ways these motions can take place, but maybe look different, okay? Wrist flexion, wrist extension, wrist flexion, wrist extension. How do I know that this is flexion extension? You follow the fingers. What's really cool, I'm gonna lecture more of this when I get into the radial ulnar joint of the wrist, but your wrist doesn't twist. Well, Campbell, what about this? Well, that's your radial ulnar joint. See when I do this, how you see motion down here? Because that's the bones that are moving. Your pinky always is going to be ulnar side, and your thumb is always going to be radial side. This doesn't twist, okay? This stays still. So my point is that when you are moving your wrist, you know where wrist flexion is because you just got to follow the fingers. Finger flexion is going to lead into wrist flexion, okay? Finger extension is going to lead into wrist extension every time. So that's what I'm trying to get to. Wrist flexion going, hey wrist, go into fetal position, is the same as, so fixed forearm, radius and ulna, movable carpal bones and phalanges. Fixed wall, movable door. Wrist flexion, wrist extension. Wrist flexion, wrist extension. Or we can have the same thing by going wrist extension, wrist flexion, wrist extension, wrist flexion. Let me show you a way I can prove that. If I start from here and go from A to B, Lafayette to Lake Charles, A to B, okay, I'm in an extended position because to go back home, I'd have to flex to go back home, right? So I know I had to have extension. We could do the same thing here. How do I know that this is extension? Because if I froze everything, you remember Gru from Despicable Me, is that it? Freeze Rick! Freeze everything. And look, if I rotate everything down without moving the joint, I get to the same position. How do I have to move to go back home? I have to flex to go back home. So I had to have extension. I'm extended here. So to be extended could either be from A to B or from A to B. So why does it look different? Why does the same change look different? It's because it's in two different global directions of spin. If you're looking at me, sometimes I forget if you're literally looking at me or a mirror image. So I'm just going to talk about this in terms of spinning from my perspective. So you may need to put yourself in my shoes, little Clint Black for you. From here to there, the wrist is spinning counterclockwise. A to B, wrist extension. But when I move the forearm, wrist extension, the forearm move clockwise. And what I'm trying to get you to see is that's okay. In fact, that should make sense. Because if you had a clock, all right, let's look at it like this. If you had a clock, I'm getting close on, 1 second, watch this clock. Okay, if you had a clock and this hand went from 6 to 9, and you say, okay, well, if it went from 6 to 9, it's spinning clockwise. Everything's fine. There was a change from here to there, clockwise 3 hours or 90 degrees. But watch this, how cool. I could also do that another way. You got to follow me here. So in this example, what I did is I fixed the clock hand and I rotated the clock. And I still got the same change. It went from 6 to 9. But instead of moving the clock hand clockwise, I moved the clock counterclockwise. But I still got the same change. It's still pointing at 9 o'clock. The same change in time happened. Move the clock hand clockwise, or keep this fixed and move the entire clock counterclockwise. Get you to the same place. Cool? All right. I think that's cool. Again, let me know if you need me to clarify that analogy. Okay, now what I'm going to do is I'm going to brush up on bones, classification of bones, and also major advantage of bones. So you guys in biology had bone labs, I'm sure, and that's where you learned about the humerus, and not just the humerus, but bony landmarks, right? So this isn't a separate bone. The head isn't a separate bone. It's just an area of a bone. Acadiana isn't a state. It's an area of a state, right? It's an area of Louisiana. So Louisiana would be the bone, and Acadiana would be a certain area of the bone. The Vermilion Bay would be an area of a bone. Sulcus is an area. A tubercle is a bony knob, right? It's like a little peninsula. So that's all that is. It's not different bones. It's just different areas on the bones. Now, these little bony nubs are very important because they serve as biomechanical advantageous pull points for muscles. So when you get to a lot of little bony knobs on there, that gives the muscles a little bit of extra mechanical advantage of pull, leverage, okay? I'll teach you all about leverage and biomechanics. So we have four, and this is all in your book, okay? This is all in your notes that I posted. But we have four major classifications of bone, and then there's some subclassifications, but you have long, short, irregular, and flat. Okay? We're going to start off with long. The long bones are the ones you move. They are optimal for movement. Of course, there's other functions of them. You know, don't they store marrow? Yes, but that's not important to biomechanics, movement stuff, okay? So long bones are great for movement. When you have long levers, you could cover a lot of room. And when you sweep your arms or leg through, you have long levers. Think about, you know, little kids when they first learn to walk. They don't cover a lot of ground. That's why it's easy to catch them. But the taller you get, the more you develop, the longer you could swing those legs through. Usain Bolt, the fastest human alive ever. He's like 6'3". He's got long levers, man. He's swinging those things through. Pitchers like the one that I pulled up here, man, movement. Having long levers. Pitchers typically, you know, have long levers that are very efficient for movement. Okay. Short bones are like, let me give you some examples, like dorsal bones. You see these little comminuted little bones in here? These are great for dissipation of force. So like you can imagine if your foot was just one big chunk of bone, you'd stress fracture or crack the heck out of it. In fact, these little comminuted bones kind of show you where the stresses are that you've kind of learned to dissipate and take off. Another way to look at it is if you were going to jump off of a one-story building, I don't want to land on wood rigid link. I don't want to land on cement. I want to land on sand. Give me something that can dissipate force, that has several little pieces that can shift and glide and move. And that's what you get with your carpals and your tarsals. You get these little shifts and glides and space and fluid, and where they can shift and glide and dissipate force. Okay. In addition, short bones are great at gliding, not just to dissipate force, but to summate force. And there's a special way that works. But it's where, think of it like this. Think of it like when you were a kid playing with dominoes. I don't know about you, but I never like played dominoes. I just played with dominoes. And I would stack the dominoes and so this is a front view. And I'd stack the dominoes and then I'd knock them over, right? You'd knock them over and they'd fall. And you'd stack them up one at a time in straight lines, but that'd get boring after a while. You'd start wanting to do tricks. And so you discover right away that you can't just curve the dominoes 90 degrees. That doesn't work. What you have to do is you have to do a gradual change. You have to do a little bit here, then a little bit there, then a little bit, then a little bit, then a little bit. The next thing you know, you're off and running in the other direction. So if that looks familiar, that's kind of how your spine works and your neck works. It's gliding. It's like a slinky. When you take a slinky and you do this, all of that motion didn't come between one joint. It came between the sum total of a bunch of little bits of a bunch of joints. A little bit here, a little bit there, a little bit here, a little bit there. Next thing you know, you did a 180. So our tarsal bones glide and shift and give us our inversion and eversion, as I'm going to teach you guys. Our vertebra glide and summate motion. Okay, so that's short bones. So we did long, we did short. So short bones, summate motion, dissipate force. Long bones, movement. They are very efficient at significant motion. Long bones give us motion. Flat bones are extremely great at defense. So we got to move and we got to defend, right? Let's think about what we need to defend. We need to defend that great computer that's in our skull. Skull. Flat. Dissipate force, protection like a shield. In addition, flat bones are great at serving as origins of muscles because there's a lot of surface area in there those muscles can attach to, okay? So a lot of facial muscles and muscles that influence the neck start on the skull because there's a lot of surface area that those muscles can start onto and cross and influence motion, okay? Let's think of some other flat bones. Your scapula, your back, your shoulder blade, it's a flat bone. Back there protecting your thorax from the back. Why? Because you don't have eyes that go in your back. So having an extra shield there in areas you can't see is great. And again, it serves as a surface area for attachments of a lot of different bones. You got a lot of muscles. I'm sorry, a surface area for attachments of muscles. You got a ton of muscles that articulate that start on your scapula, as we're going to see in biomechanics. Let's think of some different kind of flat bones that serve as protection. Your ribs. Your ribs. Think of your ribs as slotted, like a slotted shield. And you think about someone's rib cage as kind of being like a shield to protect your internal organs. And of course, there's slots in there because you got to breathe, and it can't be a rigid shield or it wouldn't be able to expand and contract, okay? But your ribs are to protect. And then a subclassification of flat is called sesamoid bones. We have some sesamoids in our thumb and our big toe, but one of the most famous sesamoids is our patella, our kneecap. So this right here, this sesamoid is a flat bone, very flat. So what does it do? Man, protection. You think about falling on your knee or even getting down on a knee. Having this patella, this flat bone, to serve as a protector of the anterior part of the knee, it's very, very important. As much time and force that we give falling on our knee, landing on our knee. And yes, it does serve as a mechanical advantage for influencing motion of our quad. I'm going to get to that in biomechanics. But it also serves the function of protection, a protector of the anterior knee. Okay? So, understanding the main function of bone is, my bad, irregular. Irregular is like the joke or the wild card. Irregular bones serve exceptionally special function. You think of the little ossicles in your ear, right? The malleus incustapes, those are very specialized bones that do very specialized things. Your mandible is an irregular bone. Your vertebra are very irregular. They serve very special niches. Your hyoid, muscles that serve very special niches are irregular. Or you could look at it as it doesn't fit one of the main categories, so we're going to toss it into a miscellaneous category. Okay. So from your previous classes, you should know what the main bones are. And from this lecture, you should know that those bones articulate to form joints, and it's those joints that have motion. That's kind of important. The bone itself isn't motion. What? It's not, because I just explained earlier that I could have knee flexion and not move the tibia at all. And I can have knee flexion and not move the femur at all. It's a concept between the marriage of multiple bones and how those things move about each other. Okay? Just because your car's tires are spinning doesn't mean you're moving, because it's a relationship between your car and the ground, whether you move or not. That makes sense? In other words, if your car was off the ground getting your oil changed and you revved the tires, you ain't going anywhere. There's no motion because it's relative to you and the ground in terms of your car. Okay? So it's very similar. Joint motions are a relative term that's relative to the bones that make up that joint. Wrist flexion, wrist flexion. Wrist extension, wrist extension. Okay? Look, I had to concentrate on that a little bit. But Those are easy. Let's get to some more complex ones. This is just to introduce you to these concepts, guys. Right transverse cervical rotation, right transverse cervical rotation. Left transverse cervical rotation, left transverse cervical rotation. Start, finish. Hey, I'm looking at my left shoulder. Start, finish. Hey, I'm looking at my left shoulder. Why does it look different? Because of the concept of global references, which again, what you guys are, it's Pavlov, ring the bell and you salivate. Man, we salivate for global references because that's what we're used to. That's what we're used to seeing. But joint motions, human motions, are locally referenced concepts. So I got to get you out of that habit of thinking if anything spins this way, it's called this, and if anything spins that way, it's called that. Okay, I'll do it one more time. Right transverse cervical rotation, that motion, looking to my right, is the same as this. That was the same motion. A to B is the exact same as A to B. From my neck's perspective of motion, it's the same thing. Okay? So you're going to see that when I lecture, when I go into specific joints, I'm going to lecture about the ankle, the knee, the hip, the whole 9 yards, more detail. But what I'm going to do is I'm going to break down motion into 4 main types. I actually hinted on this in an early lecture, but I love repeating myself. It looks like it's moving, and it is. Right? It looks like it's moving, and it is. That might be the motions you guys were introduced to, and that's great. There's nothing wrong with that. That's easy. Another easy one is it looks like it's not moving, and it's not. Right? Nothing happens. Here's the ones that can get tricky. It looks like it's moving, but it's not. So let's say I learn right transverse cervical rotation is me looking to my right. I'm not going to teach you to do that because if you use global concepts, it's going to get you into getting tricked. If everybody's ever heard Campbell's class is tricky, I'm not tricky. Global and local references are tricky. I'm trying to get you to work through that. It looks like it's moving and it's not. Imagine if I had a halo, which is a structure meant to eliminate neck motion. If somebody gets hurt and they don't want you to move your neck, they'll basically put you like in a neck brace. But it's a halo. They don't let you move. So I can move my whole body and look to the right. But my neck stayed in anatomical position. Notice this is a lot different than moving my whole body. So if you go off of a global reference, when Campbell looks to his right, that's right transverse cervical rotation. It looks like it's moving, but it's not. My cervical vertebra stayed in its anatomical position. Okay. Another one that's tricky is it looks like it's not moving, but it is, and that's the one I gave you here. Whoa, he didn't look to the right, or he didn't look to the left. His eyes stayed forward globally. But here's one way to prove. I'm going to prove to you that my neck had motion. If I started off in anatomical position and I did this, yes or no, am I still in anatomical position? No, Dr. Campbell, you're not. That's right, voice in my head. So the next question is if I'm not in anatomical position, how would I have to move my neck to go back home? I would have to spin my head to the right to go back home, which tells me I had to spin my head to the left when I left home. So from here to there is left transverse cervical rotation. And how do I know? Because if I started in Lafayette and ended in Baton Rouge, I had to travel east. If I started in anatomical and I end by looking at my left shoulder, I had to spin to the left. Isn't this going to be fun? So, after this lecture, I'm going to get into sagittal plane joints of the body, because I'm going to use fetal position as a way to really etch into your head how this stuff works. So we're going to be doing a lot of flexed, extended, flexion, extension. I'm going to also teach you in the next lecture how we infer motion with still pictures. Because you may be like, well, dude, how are you going to ask questions with photos? And I'm going to teach you that. I'm going to teach you that we can have one picture and I use anatomical position. Think of it like this. If we know Lafayette is home and I send a picture of you in Baton Rouge and I say, okay, you're in Baton Rouge. You are leaving home and you're in Baton Rouge. How'd you have to be moving? Well, leaving home, Baton Rouge, you're traveling east. If I have a picture of you in Baton Rouge and I say, you're coming home, well, you're traveling west. It's the same thing with joints. If I give you a picture and the person is flexed, and I say you are moving towards anatomical position, then you know you have to be extending. And if I say you're flexed, but you're moving away from anatomical position, you know you have to be flexing. An easier way is before and after photos. So you could have one photo and then use anatomical position as a means to infer whether you're going towards home or away from home. So you can infer motion like that. An easier way is a before and after picture. The first photo may be here, start, and then the next photo may be here, finish. And you say, okay, well, if I go from here to there, I had to have knee flexion. From here to there, I had to have knee flexion. So before and after photos. You have some of those in your support materials, okay? So I hope everybody's doing well. Again, 24 hours access to office hours, virtual office hours. Text me, email me. We'll find a mutual agreed upon time to talk about it. I hope everybody's doing well, and I hope you learned something today. Bye-bye.